In this video, we'll calculate an approximation to a double integral, and we'll also calculate an exact value for the double integral. So whereas single integrals yield areas under a curve, double integrals will yield volumes under a surface. Now we want to estimate the volume of a solid that lies between the surface and the xy plane. And the area below the volume is actually an important area called R. It's a rectangular region, and this is the region above which all the volume of the solid lies. Now our rectangular region is going to go from an x of -2 to an x of 2. And also it's going to go from a y of 0 to a y of 2. So the line back here will be y equals 0. And then this line here will be y equals 2. Now over here, in the other dimensions, we'll have x equals -2. And then up here, we'll have x equals 2. So let's sketch the region R inside this table. Here's a drawing of the rectangular region R. There will be 15 boxes in all. And we'll take these points as the points with which to plug into the function and get a height. So I'll start off with the coordinates of 0, 0. And I'm just going to plug in to the formula 4 minus x squared plus y. So that is clearly going to be 4. And I'll plug in the x of 1 and a y of 0. And we'll get 3 for that. If I plug in an x of -1 and a y of 0, I also get 3. If we plug in an x of 2 and a y of 0, we'll get 0. And there's some symmetry to this shape. Next, we're going to add y to the same values that we had here. So we'll get 1, 4, 5, 4, 1, and then finally 2, 5, 6, 5, 2. So if we were to plot these dots onto this shape here, they would look basically like this. You got 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. 1, 2, 3, 4, 5. And we're just going to create vertical boxes. Okay, so they're basically going to have a length and a width and a height. Now all the boxes are going to have a length and a width of 1. So that's a 1 and that's a 1. But how tall are the boxes? The heights are given by the function values, and those are the numbers in this table. So in order to estimate the volume, what I could say is this. The volume is approximately 2 plus 5 plus 6 plus 5 plus 2 plus 1 plus 4 plus 5 plus 4 plus 1 plus 0 plus 3 plus 4 plus 3 plus 0. It makes 45 cubic units. Each of these squares represents what's called a delta or dA. And remember that the height is f of xi comma yi. So what we've really found here is a sum of f of xi comma yi times delta A. It's a volume. And in our particular problem, we have 15 different boxes. So we're going to go from I equals 1 to 15. And it's 45. So now what we can do is we can put down a rectangular grid on the xy plane showing the bounds of the region R. We said we wanted to go from x of negative 2 to a x of positive 2. We also want to go from a y of 0 to a y of 2. And this says draw two rectangles inside the region R. So we want to draw actually a similar situation as is shown here. So we want two rectangles. Now what we'll do is we'll use the midpoints of the rectangles as the xi comma yi, and the other one can be an x2 comma y2. We want to use those coordinates to find the height of the function. And that's what the question at the bottom says. The question at the bottom says, an approximation of the total volume of the solid would be the sum of the volumes of these two prisms. Estimate the total volume under the surface using n equals 2. So the first thing I'm going to want to do is just find what is x1 comma y1. And then I'll find x2 comma y2. So we got negative 1 comma 1 and 1 comma 1. Now we want to find what is f of x1 comma y1. And then we'll multiply it by the area of that square. Then we'll multiply f of x2 comma y2 times delta A2. All right, so f of negative 1 comma 1 would be 4 minus negative 1 squared plus 1. which is 4. And f of 1 comma 1 would be the same. All right, so the sum from I equals 1 to 2 of f of xi comma yi delta a is, all right, so we also need to know what our delta a is. Our delta a is 2 times 2. Each box has a height of 2 and a width of 2. So delta a is actually 4 for both of them. So when we go to fill in the formula, we need 4 times 4 plus 4 times 4, which is 32. Now, it may not be the best approximation of the volume under this surface because our boxes are so big. Even if you go back up here, our boxes were much smaller. And here we found a volume of 45. Now, if we consider the rectangular region R, we could write the problem as a double Riemann sum. In R, we have m rectangles in the x direction and n rectangles in the y direction. So how many total rectangular boxes do we have? Well, we only have 2 total rectangular boxes in this first attempt. But what if we use 8? On the right, draw 8 rectangles inside the region R that would match up with the picture. We still want to go from x equals -2 to x equals 2. And we have to go from y equals 0 to y equals 2. But they want 8 boxes this time. So let's divide it this way. Let's identify first the midpoints of each box. Now we'll evaluate the function. We need to find f of -1.5 comma 1.5. And remember, the formula was this. We get 3.25 for that. Now by symmetry, this one's going to have the same height. Now let's try f of -0.5 comma 1.5. 5.25. So that takes care of the top row. Okay, so those are all the heights that we need. Now, in order to complete our sum, we're going to need to multiply all these heights by the areas of these rectangles. But luckily, these areas are all 1. Our delta A's are 1. So our sum is going to go from I equals 1 to 8 of f of xi comma yi delta A. And it's going to be the sum of all those numbers. I get 30. If this process were to continue, and the number of square subdivisions n approaches a limit of infinity, then we'll be able to find the true volume under that surface. Notice that in my first attempt, the surface area of my object would have been substantially bigger than r. We need the surface area of our shape to be exactly equal to r. And at least we did achieve that here with this type of approximation. I didn't go beyond the -2 to 2 and 0 to 2 bounds. And same thing here. I didn't go beyond those bounds. But we need more rectangles. We need an infinite number of rectangles. And we can achieve this with a double integral. So a double integral can be used to integrate a function of 2 variables over a region R. The result will be the signed volume between the surface and the region R in the xy plane. Notice that for a rectangular infinitesimal area dA, dA would be a product of an infinitesimal change in x and an infinitesimal change in y. What that means is if we have a square of infinitely small area dA, then that dA would be a product of dx and dy. So we have this is an important identity that we can work with. dA equals dx times dy, as long as it's a rectangle. Using this, we can create limits for our double integral. We can integrate with respect to the x-axis first, and then we can integrate with respect to the y-axis, or vice versa. Now it's important that in a double integral, the inside limits have to match the inside differential. So if the first differential listed was dx, then the inside limits should also be x limits. Let's try this now. Let's try to set up the actual double integral here. Now we can always write this just to get started. That is just the general form of a double integral where you're integrating over the region R. The little subscript here means that R is the region of integration. And we don't have to have any limits just yet. Now once we go ahead and plug in the function 4 minus x squared plus y dA, we now see that our variables in question are x and y, but our differential variable is a. And we want to get rid of that mismatch, so we want to replace dA with dx dy or else dy dx. Now the order of integration can often be reversed, and you could do it either way. So I'll leave some space here. I'll do it this way, dx dy. Now since I chose to put the dx first, I have to use x limits here on my inner integral. And I'll use y limits on my outer integral. Now where do we want to go from and to? We want to go from x of negative 2 to x of 2. That should make sense. And for our y's, we want to go from y equals 0 to y equals 2. All right, so our next step is to actually carry out the integration. But we first want to do it on the inner integral. They're like parentheses, and we got to do this one first. And when we do it, we will treat y as a constant and just focus on x. So our antiderivative will be 4x minus x cubed over 3 plus yx. We want to come in and put our brackets around it and then move our limits to here and then bring down everything that remains. Now we'll plug in according to the fundamental theorem. Okay, we'll see if we can simplify a little. And I'll move over here. Okay, now that we simplified it, it turned into just a single integral. And we want to now integrate with respect to the y variable. Okay, I get 29.3. We can check our work in Symbolab. Symbolab is capable of performing double integrals too. And there we go. We got it right. That is the exact volume under the surface.